Good afternoon everyone and welcome to Fire. Now, let us assume that the source is not an ideal source, you have some source resistance. So, in general it may be driven by some other amplifier stage, right. So, it may be coming from some other common source amplifier or differential amplifier, and we know that output port of such amplifier you may represent it as say output port of an amplifier, any other amplifier you can represent it as a current source and the corresponding RO which is going to the next stage. I can also represent it as equivalent voltage source VO and RS. So, in general when one of the amplifier is being driven by the previous stage, suppose this is going to the next stage amplifier that we are right now considering, this is my active load common source amplifier, this is my common source amplifier and it is getting signals from the previous stage. So, I can model that previous stage as equivalent Thevenin model where the output signal is in series with the RS, the source resistance, effective source resistance of the previous stage. So, I can represent you have the DC bias. Again we are not going to detail how you are getting this DC bias. Suppose somehow you are able to bias the gate voltage, and then on the top of that you have the signal swing, the AC signal with source resistance. So, you are having the R signal over here which is capturing this source resistance. Now, in this case how do we find out the frequency response, high frequency response? For that we have seen yesterday the shortcut to do this is to find out the RC time constants at the circuit nodes. So, in this circuit we have already seen that this VGP is a constant, this is a DC value ideally. So, I can comfortably treat this as an AC ground. So, AC point of view, AC equivalent circuit if I want to draw, the VGP is at AC ground, the source of the M1, M2 is also at AC ground because connected to VDD. I am setting the capital VG to 0 for AC analysis. So, you are having R signal and you are having VG, source is AC ground. This is the AC equivalent circuit at low frequency. Now, if I want to go for higher frequency and capture the effect of the parasitic capacitances, once again I need to draw the various capacitances contributed by M1 and M2. Now, consider that the substrate of M1 is grounded. We have seen that for NMOS the substrate should be at the lowest potential ground in the IC, and likewise for the PMOS the substrate should be at the highest potential, that is also VDD, so that is also ground. So, that eliminates one of our capacitances between the body and the source. So, the CSB is eliminated because of this AC ground. You may have DC potential between the body and the source, but both of them are constant, they are fixed to DC potentials, and as a result both of them are AC ground. So, there is no AC potential, there is no change in this potential across S and VB. As a result the small signal VSB is 0 and I do not need to care about the effective small signal capacitance between Vs and Vb. What I need to take care of others, which is CGD1. Now, CGS1 is appearing between gate and the source, which is once again AC ground, and finally we have the CDB1 appearing between drain and body, which is once again AC ground. So, this is also appearing effectively between drain and body AC ground. Likewise, for M2 once again you have the CGD2 which is the drain and the AC ground, and likewise at this node I have the CDB2 between the drain and the body terminal of M2, which is again an AC ground, right. So, if I further want to simplify this complicated looking high frequency model, I can redraw this circuit a little bit with simplified capacitance. So, if I look at the CGD2 at this node, that is appearing between the drain and AC ground, also CDB2 is appearing between drain and AC ground. So, basically we have an effective capacitance at this node between CGD2 plus CDB2. Likewise, I have the CDB1 appearing between this node and AC ground. So, what we can say is CGD2 plus CDB2 plus CDB1 is the effective small signal capacitance between this node and AC ground. So, I can write this as total combined value CGD2 plus CDB2 plus CDB1. On the input side, we have CGS1 between the gate and the AC ground. So, this is CGS1, and then we also have CGD1 which is appearing between the gate and the drain. So, we have this CGD1 between the gate and the drain, and then we have the RS, R signal, and the signal source. Now, we have seen yesterday how to tackle small signal capacitance appearing between two nodes. We want to reduce the circuit to a simplified equivalent AC model, where we are having small signal capacitances appearing between the unknown node voltages and AC ground. We do not want small signal capacitances between two unknown node voltages. So, here once again I can apply Miller law on CGD1 and further simplify the circuit. So, at the output finally, if I break this CGD1 into an equivalent capacitor, I get, remember, 1 plus A with 1 plus mod A. So, this is going to be 1 plus, in this case, GM RO by 2, or basically more accurately RO1 parallel RO2 times CGD1 coming into picture, and plus all the previous term, which is CGD2 plus CDB2 plus CDB1. Sorry, I am just sorry, this is I have just written the opposite thing. So, here it is 1 upon, whereas on the opposite side, on the source terminal, we have CGS 1, and here we get the 1 plus A. On the other side, we get 1 plus 1 upon mod A. Here we have the equivalent capacitance coming as 1 plus GM 1 RO1 parallel RO2 times CGD 1, and this is my equivalent capacitance at this particular node. So, what I have done is I have found out the small signal capacitance between my two nodes and AC ground. And now, the remaining task is to find out the small signal resistance between the two nodes and AC ground. That is going to give me the RC time constant at the two nodes, at the first node and the second node, and that is going to give me the two poles. So, remember what we did in the last class was, we have the low frequency gain of the amplifier, which is minus GM RO1 parallel RO2. This is multiplied by the two factors, the two poles, because in this circuit node, in this circuit we have two nodes. So, this gets multiplied by 1 plus S upon P1 and 1 plus S upon P2, where P1 and P2 are 1 upon R equivalent 1 times C equivalent 1. So, we have found out C equivalent 1, what is the equivalent small signal capacitance between the node 1 and AC ground. Likewise, we have to find out R equivalent 1. So, what is the R equivalent 1 between this node and AC ground? Looking into the gate, MOSFET has infinite impedance ideally. So, infinite small signal resistance looking into the gate. On the other side, we have small signal resistance equal to R signal, that is between the gate and the AC ground, that is R signal. So, I can just say this is going to be R signal. What about P2? What is 1 upon R equivalent to So, C equivalent to we have already found out. So, this is the expression for C equivalent to which is given, and I also need to find out what is the R equivalent to. So, once again if I go back to my small signal model and I try to see what is the small signal resistance between the drain node, that is this output node, and the AC ground, that is once again just going to be parallel combination of RO1 and RO2. So, R equivalent to, that is a small signal resistance between drain and AC ground, that is just RO1 parallel RO2. So, here we write R equivalent to is RO1 parallel RO2. So, this gives me the value of the two poles we are looking at. Now, depending upon the circuit, one of these poles can be higher, another one can be lower. So, for example, if this previous stage happens to be a common source amplifier or a differential amplifier with resistive load, where the load resistance is pretty small, maybe 1 kilo ohm, 2 kilo ohm. So, in that case, despite this capacitor being large, despite having a large multiplication for this CGD1 here and resulting in effectively large CG, let me call this CG, total value CG, and let me call this total value CD. So, despite having this large multiplication, Miller multiplication, if I having R signal small, suppose the output impedance of the previous stage is small, this can still be higher. But in general, if it is being driven by a similar stage with this kind of active load, the previous stage is also having similar output resistance RO1 parallel RO2, and here you are having large Miller multiplication. As a result, this can be the dominant pole, because this can be the lower frequency as compared to P2, where the total capacitance is relatively small. So, if I assume that the R equivalent at these two nodes are similar, in that case this node is going to give us dominant pole because of this Miller multiplication factor. So, once again this is going to be the frequency limiting or bandwidth limiting node, because if this is a high impedance source, R signal is high coming from a previous stage which is having relatively large output resistance, we are going to have RC time constant over here large because of its Miller multiplication factor, and as a result this node determines my 3 dB cutoff frequency. This is the lower of the two poles. So, we will cover how to get the board plot and do the stability analysis for multi-pole, that we have not covered. Yesterday we just looked into the 3 dB cutoff frequency for a single pole system, and we looked at the 20 dB roll off that happens after the first pole. But in case of multiple poles, once again you have 20 dB, and after the second pole you have 40 dB per decade slope. Those things we will be covering tomorrow when we get to the stability analysis of our feedback amplifier for the front end. Now, this is about the frequency response, and as we did last time, we are now going to look at the noise analysis. So, whatever we are doing here, it is going to be directly applicable in the design of our differential amplifiers or the two stage amplifiers, op amps. So, this is we will not repeat all these analysis, we will just remind you that this is the thing we have already covered, and we will use the result that we have obtained over here. So, now let us look at the noise analysis. So, now I can once again redraw my circuit. Now, I am not drawing the reference branch, remember. So, in our previous analysis we have seen that the reference branch is constant DC voltage, this is AC ground. So, I am not drawing the reference branch, this is the reference branch of the current mirror. I am just ignoring this because this is the DC potential ideally. So, let us just draw the two transistors, the load transistor and the input device, and now we are trying to see the effect of the noise sources in these two transistors. What we have seen yesterday, the noise sources, you have the channel current noise, call this M1, call this M2, this is 4 kT gamma GM1. Now, gamma can also be different definitely. So, we can call it gamma 1 GM1, does not matter, this is a constant quantity. And likewise, you have the channel current noise for M2, again 4 kT gamma GM2, and likewise you have the noise voltages 1 upon f noise sources, k upon f COX W L W1 L1. Again k can be different, k1 k2, we can write this as k1 k2, but does not matter in the analysis. we are just looking at the parameter on which we have control, that is the W by L ratios and the GM. And then once again here you have K upon F COX W2 L2. Now, we have seen that if the source is at AC ground, I can reflect this small signal noise source at the gate into an equivalent drain current. So, I can capture the effect of this noise voltage at the gate in form of drain current by multiplying this voltage by GM square, because remember this is the mean square values of spectral density. So, I can just multiply this by GM square and reflect it as a current. So, if I take it in the form of a current source and I add this in parallel with the noise current produced by the channel, I can add the term K upon F COX W2 L2 times GM2 square. Likewise, if I try to reflect this in the form of another parallel current source, I can add the term K upon F COX W1 L1 times GM1 square. So, in that case I have just 4 current sources with mean square values given by these expressions. And now, if I look at the small signal, even without drawing the small signal, I can find out what is the small signal voltage, because if these are the total small signal currents flowing between drain and source, in the AC analysis what are we going to get at this node? We are going to have the small signal resistance of these two MOSFETs M2 and M1 coming in parallel, just like we did in the previous case. So, since we have reflected these noise voltages on the drain side in form of current, so now these two become AC ground. So, at the input side M1 I can just put an AC ground over here, and here I have captured the total noise current because of M1 by multiplying the input source by GM square, and likewise, so I can call it IN1 square, and likewise I have also captured IN2 square, and we know from drain to source we are going to have the RO of M1 between drain and AC ground. Likewise, we are going to have RO of M2, that is RO2 between drain and once again AC ground, which is VDD. So, once again you have RO1 parallel RO2, and if you have to multiply and get the voltage, remember this is IN1 square, IN2 square, we want to get the VON square over here. So, we need to multiply this by RO1 parallel RO2 square. So, I can just write down the total current equation, total equations for the VON square, which is just going to be RO1 parallel RO2 square multiplied by IN1 square plus IN2 square. Now, if I just expand this, now once again another concept that we have seen yesterday is the concept of input referred noise, where we want to compare the overall noise produced by this circuit with the input signal appearing at the gate. So, if we can reflect this total VON square to the input port, then we can compare this total noise produced by this circuit with the input signal. That is the standard way of quantifying the noise in the circuit. We can get the magnitude of input referred noise, and to do that we need to multiply this VON square by the gain of this circuit. So, what is the small signal gain of this circuit from the gate to the drain? That is just GM square times RO1 parallel RO2 square. So, AV square, if I look at the magnitude of the gain square, that is just GM1 square RO1 parallel RO2 square. Therefore, I need to divide this entire equation by GM1 square RO1 parallel RO2 square. Therefore, this RO1 parallel RO2 square anyway goes away, I am just left with 1 upon GM1 square. So, I have to basically divide this entire equation by GM1 square. Let me do that. 4 kT gamma GM2 upon GM1 square plus 4 kT gamma upon GM1 plus K GM2 square upon GM1 square F COX W2 L2 plus K upon F COX W1 L1. Now, if I go further and try to look at the device parameters, like how GM1 and GM2 are dependent upon the sizes of the transistors, and try to figure out from there how the overall input referred noise of this circuit can be minimized. What are the design parameters? That is basically W by L and GM. Once again, GM depends upon ID. So, that as designers we have these options in hand. We have the GM1, GM2 in hand, we have the W and L in hand. So, we need to make appropriate choices for these parameters, so that this term can be minimized. So, to do that we need to convert these GM1, GM2 into the parameters on which it depends, which are basically W, L of the devices and the ID. So, what is GM2 equal to? So, GM2, if I write down GM2 square W by L 2 times ID W by L mu P COX, or I can call it W2 L2 W2 by L2 ID mu P COX. And what is GM1 equal to? 2 times W by L1 times ID mu N COX. So, COX goes away, we have ID going away. If I assume mu N and mu P are closed, we can get rid of those as well, which are, because they are not really in our hand. We are more interested in looking at the dependency on the parameters which are in our hand. We see that W2 also goes away in this term, W2 also goes away. We are going to get L2 square in the denominator. So, L2 over here, L2 over here, L2 square in the denominator, and W by L1 in the denominator. This is the story of this term, which is relatively the most complicated term. Other terms is simple to see. This is just GM1. So, basically we are going to get root under W by L1 ID1, and likewise GM2 upon GM1 square once again over here. So, once again W by L1 over here. So, if I further simplify this, so I can write down 4 kT gamma. Now, these two quantities ID gets cancelled, and therefore, you are left with COX mu. Suppose I assume they are constant, we are just left with W by L 2, and here sorry, it does not get cancelled. You have, suppose, mu N COX and ID goes to the denominator. We have GM1 square as 2 ID W by L. So, you have W by L 1 and you are having root under ID coming over here, and you have the COX and the mu P coming over here. This is the first term. Second is 4 kT gamma upon GM. I do not need to simplify this, because GM1 I know dependencies on W by L and ID. This term, once again I have K times W upon L. Let me use a separate W by L1 times L2 square. This is what I am getting in the denominator, and likewise the last term is K upon F COX W1 L1. So, let me write it a little more clearly, so that, so let me just copy this, and then from there try to conclude what is going to happen to the overall noise expression. So, here once again 4 kT gamma W upon L2 mu N COX upon root under ID W upon L1 2 COX times mu P plus 4 kT gamma upon GM1 plus K upon 2 W by L1 L2 square plus K upon F COX W1 L1. So, and of course, in the first term also you have the f term, the frequency dependent term. So, these two are the frequency dependent term 1 upon f, and these two are the white noise term. So, yesterday we have talked about the concept of corner frequency, where the white noise term and the 1 upon f term meet. So, if I say this is your VIN or VIN square, which is the mean square of input referred noise per hertz, and this is the frequency. This is the corner frequency at which the 1 upon f term over here becomes equal to the white noise term. This is independent of frequency. This level, constant level, is going to be proportional to the first two term, right. So, if I say this term is going to depend upon the first two term. Now, if I say what is the dependency on these device parameters of W by L1 and 2. So, here if I look at the 1 upon f terms, we see that it is advantageous to go for larger W and L for the input device. So, input device, if I am making the W and L large, I can possibly get a larger a smaller 1 upon f noise. But if I make L1 large, then you see here the L1 is going to come into denominator. So, making L1 large may not be a very good option. I can make rather W1 large. So, to minimize this term as well as this term, I can rely on making W1 large, because if I make L1 large, second term is probably going to make problem, create problem. L1 will be coming in the numerator. L2 square is coming over here. L2 is also coming as 1 upon root L2 in the first term. So, definitely it gives us a clear hint that if I make L2 large, the 1 upon f noise over here is going to be suppressed, and therefore, we can reduce the increase the slope, and therefore, reduce the 1 upon f noise of this term. So, definitely we can try to make the L2 over here relatively large. This also tells us that W by L1, we can try to keep it large so that this term is suppressed. So, I can try to keep W by L1 large, I can try to keep L2 large. Likewise, for getting larger W by L1, definitely I can keep W1 large. The term over here tells us that larger GM1 is going to suppress my white noise floor. So, this is the white noise floor. If I make the GM1 larger, which is either increasing the ID1 or increasing the W by L1 once again. So, either I can make ID1 large, or I can make W by L1 large to increase the GM1 and hence reduce this floor further. And same thing in the second term, W by N large, ID large, basically coming from GM1. I can afford to increase GM1, that is increase the W by L1 and keep the ID slightly larger to reduce my noise floor, white noise floor. So, basically by following these design steps, we can try to push this noise floor down. I can also increase the slope of the 1 upon f noise term, so that the corner frequency is also pushed away. These are the favorable design steps or the directions to reduce the overall white noise as well as the 1 upon f noise for the system. So far, we have not considered what is the significance of this 1 upon f noise. We have just said that the signal that we are interested in processing may lie very well in this domain, which can be very strongly corrupted by the 1 upon f noise. We will see that how this choice of this corner frequency is going to affect our front end amplifier design when we look at techniques to mitigate this 1 upon f noise using chopper stabilization technique little later. So, we will come back to this concept of 1 upon f noise and try to see we are trying to minimize this thermal noise, that is the white noise floor, and also the you are trying to push the corner frequency further. What are the pros and cons? So, definitely here at least we have the starting point, we have some information regarding the device parameters that are in our hand and the circuit parameters that are in our hand, that is the W by L of the input device, the channel length of the output device, and the bias current. So, these are the parameters which are affecting my noise. So, of course, again we see that there is going to be trade off, right. If you are increasing the ID to reduce the noise, what are the two things that are going to happen? We have just seen increasing noise reduces the gain, mod AV will reduce, Likewise, increasing the ID, power consumption will increase. Bandwidth may also improve, but bandwidth is increasing, that is a good point, but the disadvantage is the power consumption increases and the gain reduces. If you are increasing the W by L, once again you are having the parasitic capacitances increasing, and therefore you are going to get reduction in the bandwidth. And likewise, if you are increasing the L2, once again parasitic capacitances as well as the resulting bandwidth will be negatively impacted. Likewise, if you are increasing the L2, we know that the signal swing at the output is again going to be impacted, because if your L2 is increased, remember what is going to happen in the current mirror. If your L2 is increased, the required VSG to produce the current I ref will be increased, therefore, the VGP will be lowered. If I am applying larger length, of course, these two transistors are supposed to be matched. So, I have to use preferably same length of M3 as well as M2, and if I am increasing the length of M2 for a given I ref, I will have lower VGP3, and that implies lower maximum allowed value of VD. So, that is going to limit my swing. So, once again we are trying to show that you are trying to minimize one parameter, that is noise. It can have effect on many other parameters, the gain, bandwidth, swing, and so on. So, when we come towards differential amplifier, we will be reusing this analysis for our design of the multi-stage operational amplifier and the front end amplifier.